Good morning, class. It's about 9 o'clock on Tuesday morning, and I thought I would record maybe a 30-minute lecture or so here and get this posted for you. I'm trying to do these in smaller bites. So this is where we finished up last time on figure 33. So the discussion of this is in the previous lecture. So we're going to start out with point 8 here, crossover, and that should say bridge. They've got a typo in the Bell and Gossett literature here. Crossover bridge to secondary circuit flow relationships. So each secondary circuit is served by a crossover bridge, which supplies necessary primary water. So here is our secondary up here. This one is somebody ran a loads program, probably a carrier program or train trace, determine if this is this is probably a heating situation. So determine what the design heat load was. And so at the design condition, we would need 100 GPM of flow, and part of the design would be the temperature in and the temperature out. They just haven't put all the information on the figure here. And so that's caused by this secondary pump that circulates the secondary loop. On the crossover bridge, we see we're sized at 20 GPM, which tells me that this water is probably much hotter coming up on your primary supply into the crossover bridge. We're going to take that water up here at the design condition. We're going to mix it. In this case, we've got 20 and coming up here, this condition on this figure is where this valve is shut, but if we're pulling 20 up here, we would have 80 bypassing, it would mix, and that would give us our design temperature that goes out to the air handler or heat exchanger up here. Okay, so the required crossover flows are established by secondary circuit heating cooling needs. So it's still this sizing in the coil that's going to determine how much flow rate we need out of the primary in order to be able to satisfy that. Okay, so we have two different basic conditions we can design for. One is where the secondary circuit temperature is equal to the primary temperature. So if that was the case here, and then whatever this flow rate is up here, this would need to be the same flow rate, or pretty close. This one could be larger, and you could be putting a little bit through the common pipe, but you have to have enough flow. If this temperature is going to be the same as this temperature, then you got to be able to get all water from the crossover bridge up here into the secondary and circulate it around. And then the other case would be if the circuit design temperature is different from the primary temperature, the secondary circuit. So in a heating situation, this may be cooler up here, and this may be really hot just because you want to minimize flows in your pipe size and your supply main and return main, that sort of thing. So those are kind of the two possibilities here. Most chill water systems are designed so that the secondary supply temperature equals the primary supply temperature. This requirement provides a very simple design rule. Primary crossover bridge flow rate should equal or slightly exceed secondary circuit design flow rate. And so, I mean, that's pretty simple. And chill water systems, we typically generate water someplace between 40 Fahrenheit and maybe 44 Fahrenheit at the chillers, and then distribute that out in a large system like Tennessee Tech. We've got underground chill water piping, and that water from the chiller plant is piped all around campus. And so we're probably going to pick up a couple, maybe even 2 degrees, something like that, before the water gets to the buildings, especially the buildings that are, fairly far away from the chiller plant. The insulation on the pipes is not perfect, and so we will pick up some heat into the distribution loop. So we typically would want to see the chill water temperature in the building as cold as possible, certainly at a design condition. And so we would basically pull that same primary water up and put it into the secondary. There would be no mixing at a T or anything. If we can get 44-degree temperature water out of the primary into the building, we want 44-degree water circulating up through the building through the coils. So that they will dehumidify as well as provide sensible cooling. Yeah, so the second little paragraph here, many chill water systems, however, I disagree with that many. I think probably not very many chill water systems. And most hot water systems, I agree with that, can be designed so that the secondary circuit design water temperature is different from the primary water temperature. A possibility for greatly decreasing crossover bridge primary circuit flows is established. And that's the idea that maybe I've got 220-degree primary water and I have much cooler water in the secondary. So I get a huge or very large delta T on the primary water, which then minimizes the flow rate that I have to provide for a given secondary heat load. The following example is stated for pump on-off control. The design principles are general and can be applied to any of the other possible control methods that we've talked about briefly, such as an injection pump, three-way valves, or two-way valves. So let's plunge on into example number 1 here. And you might want to get your calculator out so we can verify some of these numbers. And so it's going to take a minute or two to a couple of minutes to talk our way through all of this. The secondary circuit is designed for 140 mean water temperature at a 20-degree drop. So mean water, that means that's the average of the secondary supply and the secondary return. Well, if it's a 20-degree drop, so, and 140 is the average, then that means what? 150 is the supply, 130 is the return, and there's the 20-degree drop. So total secondary load is 200,000. So MBH is 1,000 BTUs per hour. So that's 200,000 BTUs per hour. Establish required crossover bridge flow rates for a series of possible water supply water temperatures ranging from 150 to 300. The circuit is diagrammed below. The flows we have are for 210 degree supply water temperature. So just to verify, we're showing 20 GPM in the secondary. So if you take your calculator, put in the 200,000 BTUs an hour, and we're going to use the approximate equation Q is equal to 500 GPM delta T. Now, as temperatures get hotter and hotter, that's not quite right because that 500 in there assumes that you have standard density water. You can do better. That's, Q equals 500 GPM delta T is the same thing as Q is equal to M dot CP delta T. We just basically changed the units. The 500 is for the difference, the flow 60, and it has I think it's 8.34 pounds mass per gallon. Well, as the water gets hotter, that 8.34 goes down because it's not quite as dense. And so the Q is equal to 500 GPM delta T becomes less accurate as the temperature of the water goes up, but we still use it anyway. And so, I just want you to realize that. So if you take your calculator and you take 200,000 BTUs an hour, which would be our calculated load, say from our carrier program, and divide it by 500, that's our conversion constants, and then divide it by the 20-degree delta T, you get 20, and that 20 is GPM. So that's where they get the 20 GPM that flows through the secondary, okay? Now that 200,000 BTUs an hour has to be supplied by the energy that goes into the crossover bridge. okay? And you can also notice that we've got 130-degree return temperature that's going back into the crossover bridge, and that's what goes into the primary return system is 130, okay? So he's suggesting 210 GPM and wants to know what the flow rate would be. Well, if you're 210 in and 130 out, then that's an 80-degree delta T on the crossover flow. And the energy dropped off still has to be 200,000 BTUs an hour. So use the same equation. Q is equal to 500 GPM delta T. And so Q is 200,000 again. Divided by 500, that's our constants, divided by 80, and voila, we get 5 GPM. So we would be supplying 5 GPM into the crossover bridge from the supply main. That 5 GPM would get pulled up into the secondary, and we would have 15 GPM then through the common pipe coming kind of in reverse direction, mixing at that T on the left on the common pipe, and then that should adjust the temperature to 150 going up through the secondary. And so you can check that. You can do a weight average. So get your calculator out. You might want to get a piece of paper and jot this down, make sure you understand it. But so if I take 210 and multiply it by the 5 GPM, that's 1050. And then I'm going to add to that 15 GPM times 130. And that total for all of that math is 3,000. And then if I divide it by the 20 GPM that's flowing through the secondary, divided by 20, I get 150. So basically it's just a weighted averaging of the flows and the temperatures. Okay, so let's move on down here and see what they're talking. He's going to walk us through this again. So step 1, determine crossover bridge temperature drop. Well, crossover bridge return water, as we said above, will equal secondary return water, and temperature in this case, it has to be 130 by looking at the diagram. Okay, so we know we got 130 going into the return on the crossover into the primary return. And then assume primary crossover bridge supply temperature is 210, then 210 minus the 130, that's the 80-degree delta T that I just mentioned. Okay, step 2, determine crossover bridge flow rate. Well, so there's the math that we talked through up above. 200,000 is the load, and you divide that by the 80, the delta T, and the 500 out of the equation, and we get 5 GPM. And this system, B&G system sizer, is a little circular. It's like a slide rule, but it's circles that are put together, and it's got a bunch of lines and temperatures and all that stuff. And you can do this kind of stuff instead of using the equation on the system sizer. But you don't have one. I've got a couple of them in the office, but I can't even get to the office right now. Okay, so step 3, determine the common piping flow rate and direction. Well, this is pretty simple, I think. So we've got 5 GPM coming up this direction. I've got 20 GPM going away. I got to come up with 15 GPM, and the only place it can come from is the common pipe flowing from right to left. So that 15 and 5 mix right there. We get 150 here. We pump it out into the system. It goes through the coil. The 150 drops 20 degrees to 130. We got 20 GPM at 130 comes back here. 5 of it goes here, and 15 of it recycles. So I think you should be pretty good on that. Let's see. In order to illustrate the general nature of crossover flow determination, a modulating three-way valve application flow diagram is shown for full load conditions and for the established conditions in the example above. So, you know, the numbers work out exactly the same. The control system is a little bit different. Here we have this three-way valve that's down here in the crossover bridge. And so, you know, at full design condition, this port would be closed and we would get the full 5 GPM up here. And now the mixing would occur at this point with the 15 coming through. That moves the common pipe up here. We mix there and go through the secondary. So you can look at that. I think that should be pretty clear. The 150 supply temperature as a mixed temperature results of the 5 GPM at 210 plus 15 GPM at 130. So you can see here's his calculation, which is pretty much what I said. And then if you want to solve that for the 150, you just divide both sides of the equation by the 20 GPM, and that will give you the mixed temperature. Okay. Now, required primary crossover flow rates are illustrated in this table below for a variety of primary supply temperatures, maintaining the other example conditions. So what they're going to do is they're going to vary this 210. Now we kind of work through the details on that one, and this is the way it works out. That one's good. Let me go back. Let me make that one smaller. There we go. That's pretty good. There we go. Okay, so you can see, I mean, if our crossover bridge temperature, supply temperature was 150, then that's the temperature in the secondary. We would need 20 GPM. And so the secondary flow is 20 throughout. If I want 150, if I'm going to supply it at 150, I got to have the whole 20 GPM. If I supply it at 170, then that cuts the crossover flow rate to 10 GPM. And I'm still pushing 20 in the secondary. And this is the common pipe, or this is the flow that has to recirculate to mix in order to temper the water to 150, which is our secondary temperature. And so at 180, that gets me down to 6.6 GPM. Still have 20 in the secondary. Now I'm recirculating 13.4. 200, I'm down to 5.7. Recirculate 14.3. 210, that's the condition we worked. Shows now I only need the 5 GPM of crossover flow, 15 recirculate. 230, I'm down to 4 with 16 recirculating. 250, I'm down to 3.4 with 16.6 recirculating. And 300 degree water, which is now classified instead of a low temperature water, would be a medium temperature water system. I would only need 2.4 GPM of water at 300 degrees in order to convey all of that heat to the secondary, and I would be recirculating 17.6 GPM. So you can see this is the power, one of the powers of primary secondary is I can get these flows down really low by jacking up this water temperature, but I can still have a relatively cool water temperature to put through my units, and it makes them more controllable. And so I don't really want that super hot water going through a coil. I could produce air so hot that I could scorch somebody. So there's multiple reasons for that. And you need some flow for distribution too. Okay. So this example illustrates one of the outstanding advantages of primary secondary pumping, that the primary circuit can be designed for very high temperature drops so that both primary pumping and pipe costs can be reduced. It should be emphasized that the primary circuit serves only a heat conveyance function and that its temperature drop or rise can be entirely different from the secondary circuit it serves. So I think we probably knocked that point home pretty good. I'll do a few more of these things. We've got some different types of control strategies. We're going to go back through here and discuss some of the characteristics. So point 9, start-stop pump control of secondary circuit. This control application is a simple adaptation of a control method proven in several million residential systems. It has been widely used in commercial control. And so, you know, we kind of went through this before, but we're going to put make some other comments here. And so they kind of circle back on some of this. But, you know, thermostat, the T in the box is a thermostat. It's in the space. Thermostat gets cold, tells pump, hey, run pump. When the pump runs, we pull water up here. Depending on the flow rate in the crossover and the flow, we could be mixing to temper, or we could not. It just depends on the design of the system. But this is going to circulate this hot water through the radiator or heat exchanger, come back, and return water will flow back into the crossover bridge. And if we're recirculating, we'll pull some back through the common pipe. Let's see what else he has to say about that. The only real difference between the residential system and its primary secondary adoption is that the heat source is the common pipe rather than a boiler. In a residence, you would just come directly out of the boiler. The secondary circuits are generally quite short, usually limited to about 200 feet maximum. This is because of the time relationship between heating of the near as opposed to heating of the far radiation. It's necessary that water flow from the primary to the secondary be absolutely prevented during pump off thermostat satisfied condition. So one issue is that when this pump is off, when the space is satisfied, we don't want any of this hot water migrating, say by natural circulation currents or anything, up through this T, and depending, it could migrate all its way all the way to the coil, and then the coil, if the fan is continuing to blow, could do some heating with the pump off. So that has been known to happen. So the note here, flow control valves prevent hot water flow as caused by gravity heads, or that's density differences, or the slight pressure drop established across a common piping when the secondary pump is off. So we will have some sort of a small pressure drop between this point and this point. And, you know, it's not impossible that could be enough to induce a small flow up here through the secondary, in which case you might lose some temperature control of the space. Let's see. There we go. Okay, so now flow control valve needed for start-stop pump control. Flow control valves are weighted check valves and are used to block flow as induced by slight common piping pressure drop or by gravity heads. They are generally needed whenever pumps are used for control. A flow control valve is statically weighted to approximately 6/10 of a foot water head. So you need more than 6/10 of a foot in order to force flow through this thing. And that's its purpose, is to not let these small heads cause flow through that secondary. It is an automatic check and anti-gravity flow operation when the stem is turned down. The valve is open and will not perform its anti-gravity flow when the stem is turned up. Just kind of if you see one of these out in the field. And so these little check valves that you see in these circuits, all of them refer to these sorts of flow control checks right here that we're talking about. Need for 2 flow control valves, start-stop pump control. And here, so we're going to talk more about this. So 2 flow control valves are generally illustrated for application with start-stop pump control of secondary circuits. This is because gravity flow can occur within a single pipe as shown in figure 39. So see, you know, the pump is off, and so all of our primary flow is just going through the crossover here, and they're showing this for the return. But so we've got relatively cold water in the secondary, and so it's going to be dense compared to this. And so this stuff is hot and less dense. And so within the single pipe connection, you can establish this little bit of a flow pattern where we put some hot water up into the secondary. That's going to continue to rise, and that over time will heat up that entire secondary. And that coil, it's possible, could still radiate into the space and put in heat when you don't want heat, because the thermostat satisfied, the pump's off, but you still continue to supply some heat to the space by this gravity type flow that can occur. Note here, during the 1920s, a great many one-pipe gravity systems were installed, attesting to the control problems that could occur because of the introduction of gravity, hot water into the secondary circuit radiation located close to the secondary circuit return riser. So typically that would happen when your radiator or coil was close to this return pipe, and this would just rise right up into it. It would get hot and would overheat the space. So a single flow control valve can be used when the secondary circuit return riser is underslung, as shown in figure 40. So you see, we've got an overhead crossover, but if we undersling or we come in from the bottom side on the secondary return, then you see this water is cooler. It's going to lay down here. You're not going to get this gravity circulation. So then, but you could into this pipe if this is coming off vertically upward. And so you would just need one of the check valves in this situation. Okay, I think that's probably enough for this one. I don't want to run these too long. So I'm going to stop this one, post it, and I'm also going to post one, some more help on this large homework problem that you guys should be working on. So with that, I'll record that next and get them both posted.